let's do the third problem. In Photoshoot, we have a grid of size n by n, 500 by 500. And inside, we investigate what square of size k by k I should choose. So where is the optimal one? So that we would maximize the sum of numbers inside. There are updates every time the number in a single cell increases by positive integer. So maybe this square was the best, but here there was value, say 7 somewhere here, but now 7 changes into 20, and because of that, maybe now there is new optimal square. So values keep growing in the grid. After every update, every modification of number changes into something bigger, we need to output what is the maximum possible sum of values inside of k by k square. Turns out that in this problem, it doesn't help to be a very strong participant because you might overkill this problem. You might do something very complicated. If you are, let's say, silver gold division, many people after reading this will start thinking about complicated two-dimensional data structures. Namely, if you want to have maximum in two-dimensional grid, something called two-dimensional segment tree might help with that. And I think it's a valid solution, but just very complicated one. Also, it will do log squared per operation. Once you learn this data structure, and in bronze, you don't even need to know what it is. Even once you learn it, you can quite safely assume that you will never use it anyway, because Olympiad problems extremely rarely have this as the intended solution. So it's more of a warning towards those of you who already know complicated data structure. Don't try to use it. In my life, and I solved thousands of problems, I used this thing maybe once. So it's very rare. Sometimes it is alternative solution, but basically never it's the intended solution. Just ugly, complicated, and slow data structure. We don't want it. So I'm not going to discuss the exact solution using it. Okay. When they are talking about 2D rectangle or grid, and we investigate sum of subrectangle, you should certainly consider 2D prefix sums. And if you don't know what that is, then certainly you should learn it if you want to get to silver division. But there is a strong reason why prefix sums will not be useful here. Actually, let me ask you, maybe somebody can tell me a reason. So do you know why not 2D prefix sums? When we have this problem that there is a grid, we are looking for maximum k by k square, and there are updates that increase some single value. Why it doesn't make sense to consider this too much? So if you get the idea, you should discard it. Why? Any ideas? The answer is that because there are updates. Because of updates. Generally, even not two-dimensional, prefix sums are a static structure. This makes sense for an array that doesn't change. If you are given one array, it doesn't change, and you have some things, some queries about ranges, the sum of a range, or sum of rectangle in 2 dimensions, then 2D prefix sums are reasonable to consider. Very often it's part of the intended solution. But if there are updates, then this is not viable. Unless we are getting into segment-free territory. So this is why that's not a solution. We will not do it. Instead, what I very briefly showed you already is some kind of a hint where 7 I changed into 20, and I said that because of that maybe the square will be in different place. Another hint is in the statement that one of the constraints is very unusual. K is up to 25. the size of this square, which suggests that we will iterate such square. We will have for loop of size 25. Also, Q is less than usual, 30,000. So from this, we could already take a guess that the time complexity is Q multiplied by K, or maybe even K squared. That, if you compute, will be maybe 50 million operations or so, which is okay. And even time complexity here is, I think, a nice hint, and it can tell you what is the intended solution. But back to this thing that I told you, it's a hint. If at some point the optimal square is somewhere, and you know that its sum is equal to something, sum equals, let's say, 300. If somewhere else in the grid value 7 changes into value 20, so now this is new updated value, it doesn't make sense to consider the square to now be in all the random places in the grid. Those things didn't change, their sums didn't change. So still here the sum is equal to 300, or maybe a square containing this value 20, so one of those few squares here, is better now. You only need to consider squares that contain the value that has just increased. And the number of such squares is k squared at most, 25 squared, because it needs to be nearby. The row is one of the previous 25 rows, and the column is one of the previous 25 columns. The top left corner of such square will be somewhere here, in one of those places. This is where the top left corner of a k by k square can be, so that the square would contain the value 20. So if you knew prefix sums and you wanted to use it, it seems that if they tell us that the value RC changes into something new, let's say it was 7, now changes to 20, you might be tempted to say that now we iterate the square, so top left corners nearby. So for something in range from r minus k plus 1 to r, for j in c minus k up to c, we here iterate the top left corner of a square that contains me. And now I consider this square, so everything from a of r ij of size k, and such square of size k, with prefix sums, you could query in constant time what is the sum. But we cannot do it because of updates. Still, I want here in constant time to know the sum here. But if I know that this thing changes from 7 to 20, then I know that the sum increases by precisely 13. 7 to 20, the difference is 13. So what I can do is I can maintain the sum for every position. For every possible top left corner or every cell, I keep the sum of a square starting here. And what I will do here is the sum starting at this position, I will increase by 13 by the difference new minus old value. And this sum is now equal to something, it only could increase. And the answer maximize with this new sum. This is what you need to do when you have an update. And after that, the variable answer, one global variable, contains the new answer. Possibly it got updated up. So you do this for a query, and just after that, you output the answer. The only here tricky thing is maybe to make sure that in those for loops, you're not moving out of bounds. I will very briefly show you my code, but I don't think it's worth discussing. Photoshoot, it's just this. I have, why do you have old value? I guess for me, array A is the sum, and old value is the elements of the grid. Then after reading the query or the update, I iterate the for loop, the backwards things. What is the top left corner? So the previous k rows and columns. And the sum starting there, I increase by the difference new value minus old value, and I maximize the answer. It's that simple. Time complexity is Q times K times K, QK squared, as I mentioned at the beginning. No data structures needed, no prefix sums. Just the main idea is that we keep at every position, every starting position, we keep the sum of values in a square starting here. This is indeed the easiest one. I would say so. For me, it was easiest. Also, for the first problem, it's easy to get some idea, but then getting all the details right was difficult. Okay, time for questions, both about this problem or about the bronze contest in general. After the questions,